Okay, Oscar. So this is how you solve a calculating the solubility of an ionic compound when a compound is common when a common ion is present. Okay, so uh, there's a couple of steps. First, what you're gonna do, as I already have, put it in here. Um, First, you're gonna find the initial concentration, which is gonna be this number right here, as you can see, uh, a thousandth of a mole, uh, 2,000th, or yeah, 2,000th of a mole. Put it here, KSP. KSP is gonna be given from this table. KSP for this solution will be PbCrO4. It's going to be 2.8 e to the negative 13 power. We plug that in here. Molar mass of the substance they're asking for, PbCrO4. We looked that up on Wolframa. That is 320. Oh shit, we didn't change that. How about we change that? 323.2 grams. Okay. Now, we have uh, our balanced equation. We have to balance the equation first, the decomposition essentially, or the ionization. You have the solid PbCrO4 that's going to break down into Pb2 plus, aqueous, and CrO4 2 minus. Chromate, or I can't remember what this is. I think it's chromate. But notice that they have a stoichiometric factor of 1, each of them. So you do two ice tables. The first ice table, you'll plug in initial for both. Essentially, in water, you won't have any ionization initially. Um, so the change is all going to come after. And the change here is just x because, as you can see, stoichiometric coefficient of 1, stoichiometric coefficient of 1 as well. These are just going to be 1x, 1x, 1x. Here, a little bit different because you have to first do the, if I'm not mistaken, you first have to do, oh no, this is the same as well. This will be the initial G13. Yeah. Yeah, this is the initial concentration um that you're given from the substance from here from Na blah 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 blah. So this is the cation that will be produced, or the initial cation that will be produced. Um, this is after equilibrium. Here we wrote down the breakdown of the solution. As you can see, again, stoichiometric coefficient of 1. Solve for the KSP. First, you have to write down the KSP expression. KSP expression here would be correctly written as these two products. You don't include the reactants because it's a solid. So these two products, this is x times x squared. So x squared equals KSP. KSP is given right here, 2.8 times 10 to the 13th power. As you can see here, it is G14th, which is this 2.8 to the 13th power, um, raised to the 1/2, which is square root of, x. Same thing, or square root of x squared to get x. This similarly, you approximate. It's a small approximation, so it's basically just F22. That will be the difference. F22, as you'll see, is this one up here, the initial change. So it's not going to be much of an initial change. So you'll have B again, 2.8 to the 13th power, negative 13th power, divided by F22, which is the initial concentration of substance right here, times, or that's going to equal your X value. As you can see, G14 divided by F22. That's your answer. So let's try plugging these values in and see if it's right. 1.7 to the negative 4, 4.5 to the negative 8. See if that's right. Yes! It is right, motherfucker!